In this video, we're going to be going over problem 6-72 to compute the resultant force at pins A, B, and C on the frame given. And this is what they call a three-member frame, and I have that crossed out, and I'm actually going to call this a two-member frame. Two-member frame because we have member BC and we have member AC. Now remember, if we have a member that is connected all the way through, that is a one member. This is one member all by itself. So what I'm going to do is I went ahead and, to save time in this video, I went ahead and drew this out. So if you need to, pause the video and do as I did, and then continue the video so we can continue the problem. So what I've done is I've drawn the free body diagram of the whole frame and of each member. Now I have the external forces or the reaction forces already drawn on the whole frame. Now when I draw those on its free body diagram of the member, those stay in the same direction. Those are in the same direction, as well as By and Bx. Now you notice on the frame itself we have this 800 Newton force acting at this point right here. Well, again, external force acting at that point right there, and it stays in the same direction. So a few things that we need to solve, and I kind of solved that, put that answer there, but we need to take that out. So show how we solve for it. So there are some things that we need to solve for. We need to solve for this length, and we need to solve for this, but I have 1.15 meters there, but we're going to go ahead and solve for those. So if I wanted to solve for x here and this length here, let's do that really fast because we know we're going to have to compute this distributed load, and we know we're going to have this x distance for this, so we have this whole distance as well. So to solve for x, or x down here, we're knowing that this is 2 meters. So I can use tangent. The tangent of 60 degrees is equal to the opposite, which we know is 2 meters, over the adjacent side, which we're going to call x. So solving this, quick review, multiply by x to get that out of the denominator. Then you're going to divide by 60 degrees, divide by 60 degrees. So our x's cancel, our tangents cancel, so we land up with x is equal to 2 meters divided by the tangent of 60 degrees. So x comes out to be 1.15 meters, and that's what I had written there earlier. We're also going to need this length here, which I've labeled L. So L is going to equal, we have the opposite side and we're trying to find the hypotenuse, so we know we're going to be using sine. So the sine of 60 degrees is equal to 2 meters over, we called that L. So again, you multiply by L, you do all that, you come up with L to be equal to, I got 2.31 meters. So I'm going to go ahead and write that in. So if I want to find this force resultant, then it's easily, I can, by now I have this length, so, and I know that it's 200 Newton meters. So this force here is 200 Newton meters times the length we just found, which was 2.3 meters. So our meters cancel, we come up with the force, and that force I got about 461 newtons. I'm also going to need to find, let's go ahead and draw that in a different color. I'm also going to need to find this component, and I'm also going to need to find this component. I know this is 60 degrees. I know that's 60 degrees, so I'm going to go ahead and draw this piece out over here. So So I've got the member that we have. I'm actually going to draw it down here. We have the member that we're looking at. We have the force that we've drawn on there, the force resultant of that distributed load, which came out to be 461 newtons. Now if I went and did something like this, where I know that this force is going to be acting down, and this force is going to be acting to the right, it's just as components, and I draw a line out, extending that out, and I draw a line extending this out, and I draw a line extending this out. Well, I know that this is 60 degrees here. And if I know this is 60 degrees, opposite vertical angles are equal. So if this is a 90-degree triangle, we would know that this is 90. So now that I have all of that written, if I've got this as 60, if this is a right angle here, we know that this would have to be 30 degrees. I'm going to write that in a different color. We know that this would have to be 30 degrees here. We also know this is a right triangle, so this has to be 60. Again, right triangle, so this is 30 degrees, so it's pretty easy to go all the way around. So that's how I came up with the angles that I'm going to be using. So to solve for these, I actually used this angle right here as 30 degrees. So if you take the cosine of 30 times the 461 newtons that I got, I'm going to come up with 400 newtons. So that's 400 newtons. And then we know that the sine of 30 is 0.5, so 461 divided by or multiplied by half, we would get 231 newtons. I'm going to go ahead and erase this just to kind of get it out of our way. And we know that this distributed load then was 200 newton meters. So that's how I got everything now. I've solved for every distance I need and so forth. Now I need to make sure that all my forces are what I need them to be, all the forces at the pins, the resultant forces. So if I'm looking at C, let's say that I'm assuming that CX is pushing on this joint right here. It's going to the left. At this point, I'm actually going to also push into that joint right there. Now over here, I'm actually going to opposite and equal, but what's it doing? It's pushing into point C. And CY here would be going down. So if I'm doing that, once I finish my free body diagrams, what I like to do is I like to see what I can do on this whole frame in order to solve for some of the resultant forces on the frame. So if I sum my moment about point A, well then BX is going through that point. So I could solve for BY. Now I can do this two ways, and I'm going to go ahead and do it both ways. So if I sum my moment at point A, it's equal to 0. I have this force is 231 newtons. And it is negative because it's going to be rotating about point A. I guess we'll get about this point. So this, I'm going to go ahead and draw that for you. That was 231 newtons. And this force here, well, that's 400 newtons. So this is half of 1.15, how it falls, because it's symmetrical. So 1.15 divided by 2. And then we're going to subtract this 400 newton force, because it's also making this beam rotate around point A in a clockwise motion. That's going to be times 1 meter. Alright? Because if this is 2 meters and this is acting in the center, we know that we'd be going up 1 meter. Plus, 1 meter times 400 newtons, plus this 800 newton force, because it would be tendency to rotate about point A in a clockwise fashion. That's times 2 meters. And then the last thing we're doing is we're solving for BY. BY times this distance from A to B is 2 plus 1.15 is that distance is 3.15 meters. All of that is equal to 0. So By, if you throw that in your calculator, comes out to be negative 338.7 newtons. Well, since it became negative 338.7 newtons, what you could do is you could actually come over here and say, alright, this is actually going in this direction at 338.7 newtons. It's actually going down. But there's another way we can do this. We can also sum our moment, and this might be more simplistic. Sum my moment about point A. Now if I take this force, I know this distance is 2.31 meters. So this perpendicular distance from here to here is actually half of 2.31. So 461 newtons times half of 2.31 over 2, and that's going to be negative because it's going to be going in the clockwise, plus the 800 times 2 meters plus By times 3.15 meters is all equal to 0. So this then is just these two combined, which you also would get By is equal to negative 338.7 newtons. So if I were to sum my forces in the Y then, I am solving now for AY. Again, this is the whole frame. I'm just going to write that up here too. The whole frame. That's pretty important that we're looking at the whole frame. Sum my forces in the Y, I get AY minus 231 newtons. Where do I get that? Well, this force right here is negative. And then my By is actually also negative 338.7 newtons. That's all equal to 0. So AY then, that's a positive value. AY comes out to be 569.97 newtons. And I'm just going to go ahead and underline those. So we're assuming this was going up, it came out positive, so we're going to leave it up as well. Now over here on this free body diagram, I'm actually going to, I think I drew that in the wrong one. Yeah, so I'm going to just erase this really quick. Sorry about that. I'm going to erase this. And let's go back to what we had here. Because I want to drive this in the right way, so I'm going to go ahead and draw. This is actually By was negative, so I'm not going to call this negative. I'm just going to call it 338.7 newtons. But I'm showing it going in the down, so it's going down because of what we solved for up here. So if I'm going to look at all of this, let's look at member BC first. Let's look at member BC. So I'm just going to put over here member BC. And what do we got? Well, if I sum my moment about point C here, that's all equal to 0. I'm going to have this negative 338.7 because it's going to be going clockwise. So negative 338.7 newtons. I said negative, and that's because it's rotating about point C times 2 meters plus Bx, which is going to make this rotate clockwise, also 2 meters. So that's going to be plus Bx times 2 meters. So I know the 2 meters are going to cancel out. I'm going to take the 338.7 newtons over. So we know that Bx is going to equal 338.7 newtons. So this is going to equal 338.7 newtons. Now, something we could look at, or the next thing that we want to look at, is I could sum my moment, or sum my forces in the x and y here. So if I sum my force in the x, and sum my force in the y. Let's do both of those. So if I sum my forces in the x, it's equal to 0. So I'm going to have 338.7 going in to the force here. So that's going to be 338.7 newtons because it's going to the right. And then I'm going to have to subtract this 800 newtons. Subtract this 800 newtons. And then I've got C, I guess I should have labeled that, CX and CY. Then I've got the CX, which is also going to be positive. So plus CX is all equal to 0. Now if we subtract 800 newtons from 338.7, I get a negative 461.3, but I take it to the other side. So CX is going to be equal to 461.3 newtons. I've got that answer, and I've got that answer. Now, summing my forces in the y, I have this negative 338.7 over here, negative 338.7 newtons, and I'm going to subtract CY plus, subtract CY is equal to 0. So CY then, if this was negative and this was negative, CY is going to be a negative 338.7 newtons. So now I have BY, BX, I have AY, I have CX, and I have CY. So if I came over here and wrote everything that I have over here, I have CX was 461.3. CY was actually going down, so these would actually change. So I'm actually just going to change that. So that's going up there, and this is going down here. So this would be negative, or 338.7 newtons going down, So we have AY. We solved for AY was 561.97. So that's 561.97. So really what we need to solve for is AX. So AX then in this is super simple. We can just sum our forces in the x direction. So this would be, remember, AC. So if I sum my forces in the x direction, I'd get 400 newtons. That's this 400 newtons right here. Minus, so I've got this subtracting this 461.3, subtract 461.3 newtons plus AX is all equal to 0. So that would be that this was AX is equal to 61.3 newtons. You could also go back to the whole frame because you would have BX as 338.7 newtons, and you have this force 400 newtons. You could also sum your forces in the x on the whole frame, and you're going to get the same answer. But the question is asking for the resultant force. It's really important that we know what we're solving for. So the force resultant, point C, the force resultant at point B, and the force resultant at point C. Now we know we're just going to use the Pythagorean theorem. So this is going to be 338.7 newtons. So we're looking at point C here, point C, and we also said that was negative, but it doesn't really matter because we're squaring it all. Plus 461.3 newtons, and that's also squared. And then we're going to take the square root of that. FRB, well, that was 338.7 newtons squared plus 338. I'm just going to put these as all pluses because it doesn't really matter if they're positive or negative in the whole scheme of things. So 61.3 newtons squared plus 569.7 newtons squared. All I'm doing is looking at each point and multiplying or taken the Pythagorean theorem to find the force resultant. So if I to do this, take the square roots of them all, the force, resultant force at C, the force resultant at B, and the force resultant at C, or A, I should say. By computing these and putting in my calculator, I get 572 newtons, 479 newtons, and 572 newtons. So those there would be my final answers, because they're asking for the force resultant at each point. So I hope this video helps. I'm going to put, there are a few more examples on the Canvas page. Make sure you take a look at them, maybe even work through them, and then watch the video. Alright, thanks.